Hello and welcome to Toddcast number 40. We're starting into a new topic if you've been doing sequentially. We're starting addition reactions. And for those of you who are looking at these while taking organic chemistry, just a little heads up, this is where the trajectory of the course changes rapidly. To date, you learned a lot of concepts, reviewed a lot of concepts, put things together in a thinking fashion. This is where we start to shift more into memorization mode. Once you have enough memorized, then we go into puzzling, if you will, synthesis, and figuring out how to turn one molecule into another through as few steps as possible. So the course transitions. If you're using these videos as a review, you already know this. And this hopefully will be just a fast blow through for you if you do it on like 1.5 times speed to see the various reactions, just remembering terms like Markovnikov, anti-Markovnikov, syn addition, anti-addition. And so I'm hopeful that this will address both groups, but it's an introduction to addition reactions. And so an addition reaction, as the name implies, is where you add something. So just like we had a substitution reaction where, lo and behold, you got one thing substituting for another, in this case, you get one molecule breaking apart into two components, and those two components adding to the two carbons of a double bond. So you need a double bond. So we have the carbon on the left, the carbon on the right. I'm going to start with what's known as an asymmetric alkene, meaning there are bulkier groups on the right side, smaller groups on the left side. I've circled the color coordination, which will go into more detail down the road of where these two will go. But if you recall, HX, strong acid, can break apart into H plus and X minus. Because a double bond has electrons, the double pi bond are electrons, electrons will react with something that has no electrons. So electrons will end up attacking the plus, not the minus. We'll go through the mechanisms as we go, but the double bonds will go, double bond electrons will go and attack whatever the plus charge, in this case H, which means H gets its choice to go to either the left carbon or right carbon. Go to either one. If you go to the movies and you're the first one to sit down, you take the better seat. Go to a restaurant, first one to sit down, you take the better seat. It's in nature of apparently atoms and people, first person to chooses the best one, and then whoever sits afterwards gets stuck with the other seat. So H will choose the less crowded side, leaving X to be stuck on the more crowded side. So I'm going to draw it now. We're going to make a big ordeal as we go, but just want to introduce this term, and it is called Markovnikov, named after the chemist that proposed this concept. So I'm going to use a phrase, and it's outdated, but there is a decent chance some of you have seen the movie Forrest Gump. So in my best Forrest Gump voice, I want to say H goes where H is, meaning the H will go where there's the most H's. Two H's here, no H's here. This carbon has a carbon and a carbon. This carbon has two H's. So H goes where H is. So I will affectionately refer to this as the Gumpnikov rule in honor of the great Forrest Gump. So H goes where H is, implying, and you have to see the movie to understand that sentence. But H will go less crowded side because it goes on first. It also go on second. Okay. Let me get rid of my writing and say addition is in essence just opposite of what we did with elimination. So with elimination, when this was anti, this H or whatever H I lose is anti to the X, you undergo E2 elimination. Acid-base reaction, if you have acid conditions, then you can protonate this and make it leave, and then those electrons go in. We learned E1 and E2. But elimination, you eliminate the group, addition, you add it back on. So addition in the forward direction, elimination in the reverse direction. Okay, we don't just add H and X, we can also add H and OH, water. It's a little tricky. Water is not terribly reactive with organic molecules. It doesn't even dissolve into most of them. So we have to facilitate it by adding something to the system. So a lot of times we stimulate this with a catalyst like acid. And so we'll go into that as we go through with it. But again, H goes on first. So it chooses less crowded side. OH is stuck going to the more crowded side. So again, this will be something known as Markovnikov addition. Hydration, one of the many reactions we'll learn in OChem, but particularly important in biology because we are a water-based species, and consequently, we do a lot of addition of water, so much so that it has its name, hydration reaction. So hydration of a pi bond or hydrolysis of a pi bond, hydration of the molecule. Hydration is the addition of water. Hydrolysis of the pi bond means the pi bond was broken and water was also broken, and the two came together. The H went to one carbon, the OH went to the other carbon. So knowing the reactions by name, absolutely imperative if you go on to biochemistry and biology classes. Knowing the reaction by mechanism, H goes on first, so H goes where H is. The Markovnikov mechanism perspective, absolutely imperative for this class. And then just knowing a whole bunch of reactions so that you can turn one molecule into the next. So simple synthesis, if I wanted to somehow go from this molecule to this molecule, but I know that OH will not really react this very well, what I could do is I could first eliminate it, get this compound, and then do additional water, do hydration of that compound. Meaning you can go from here to here by way of elimination, and addition. And you're going to see a lot of synthetic chemistry is based on that concept. If you can't substitute one thing for another, then you go through an intermediate molecule and make it a two-step process instead of one. Okay, so a little more detail. I want to look at this from a thermo standpoint. I'm starting with two molecules, an alkene and HX, and I'm finishing with one molecule. And although technically there's solvation to consider, and that does play a role, I'm going to ignore it for now and just look at the very, very fundamental two molecules to one molecule, which means from an entropy standpoint, you're going from 2 to 1, you're getting more ordered, less chaos. So that is entropically unfavorable, meaning delta S is less than 0, negative number. But you're breaking a pi bond and a sigma bond to form a sigma and a sigma bond. So pi bonds are weak. So if you break weak and medium to form medium and medium, you break weak to form strong, you're going downhill energetically. It is exothermic, so delta H is less than 0. And delta G, the favorability or the free energy of a reaction, depends on both delta S and delta H. So we need to consider the equation delta G equals delta H minus T delta S. So if this is a negative number, which it is, and if this is a negative number, which it is, that means minus a minus is plus. So a minus number plus another number means I'm uncertain of how it'll turn out. If delta H is significant, then T delta S will be trivial and overall it'll be a negative number. If T delta S is significant, then small number minus bigger number ultimately will, minus some larger magnitude negative number is going to overall be positive and be unfavorable. So it ends up at low temperature when T is very small, then in this case, it's going to be favorable because delta G is negative. So a large negative number minus a minus or plus a smaller number is overall negative. But at higher temperature, it's going to favor this because this number becomes more significant. And we just relearned something we already knew. Elimination reactions require heat to drive them in that direction. You're forming less stable bonds, so to overcome the delta H, you have to pump energy in. And then from a thermodynamic standpoint, if you understand this equation, you're also pushing the entropic factor of delta G, which will make this one go in the forward direction. So at room temperature, you can do addition, heat it up, and you can go back to elimination. We also control it by what reagents we use, what catalysts we use to make these various reactions occur. But that's in a nutshell. So welcome to the next phase of your learning. Want to look at each of these reactions, just the memorization of what happens, but going to really start emphasizing the concept of the mechanism, how we make this occur. As I mentioned, water is neutral, so you have to start designing a reaction. A neutral molecule that's relatively insoluble in a lipid, an oil, an organic molecule, it's going to be hard to carry out. So what we have to do is we have to spice it up. So we have to add a catalyst, number one, to help it get facilitated. And that's why you see the word strong acid there. You cannot do this reaction just with water. You have to add a strong acid. So the acid will actually protonate here. Water will attack it, and then you'll lose the H plus and regenerate the acid. The catalyst is regenerated at the end to go in the forward direction. Okay. As mentioned, if you heat it up, it can go backwards. Cool it down, it goes in the forward direction. But we also control it in a second way. So if you want the reaction to go in the forward direction, you learn this from the Chantier's principle. If you add reactants, it pushes reaction in the forward direction. If you remove reactants, it pulls it back towards the reactant side. So we can push it by one of two ways. We can heat it up, that'll push it backwards, or cool it down, that'll push it forward. Or we can add water to push it forward in the presence of acid. Without any water present, we add acid, it will bring it back this way. So it'll push forward to generate the water, keep on driving the water away. The reaction will keep on going this direction. So we're going to drive things by equilibrium distribution, adding and or removing reactants and products, or temperature, heating and cooling to push reactions. So this is where all that general chemistry you learned in a very specific manner becomes now a more conceptual perspective. So if I want to maximize the yield of this or the yield of this, if I want to make a reaction where I'm trying to get an alcohol, or if I want to make a reaction where I'm trying to get an alkene, understanding that if I were to heat it up and do it in the absence of water, I'll push it in this direction. If I do it at room temperature or lower temperatures and I add water with a strong acid, douse it with water, I can push it in that direction. So you can control the distribution of your reaction by taking advantage of Le Chatelier's principle and thermodynamics, the temperature. Okay. The second thing that's new, so understanding how to manipulate reactions using your chemistry information is key, but also what's important is memorization. And memorization is made easier in OChem by being very, very organized. I'm going to introduce something called the spider chart. It's going to be very simple. I'm going to start with a molecule in the middle. By the time we're done, we're going to have 1, 2, 3, 4, 5, 6, 7, 8 different reactions it does. And we pick one molecule. Specifically, I picked something that's asymmetric, meaning one side has a carbon for the ring and a CH3. The side has carbon for ring, but an H on this side. So they are unequal in terms of substitution. When we add strong acids such as sulfuric in water, if we do it at a low enough temperature, we can hydrolyze this. And you have to keep in mind, H goes on first. H goes where H is. So I start with an H here. So that H is going to end up on that same carbon. Get rid of my mechanism and just write the result. I have not shown the H that's gone on here, but this has two H's when before it only had one. OH goes here. Point of interest, there is no chiral center here, so I could have easily put the OH in front and CH3 in back. I have honestly no idea why I did it this way, not the other, but just note this is achiral, and it's important that you write yourself notes as you think about it, because when you review it, that'll be helpful. Okay, the other reaction we did was we added HX. So I'm specifically going to do HBr. I could also do HCl or HI, but I'm going to do HBr. We have to have a nonpolar solvent for this to occur. So CCl4, carbon tetrachloride, nice nonpolar solvent. HBr dissolves into it. This compound will dissolve into it. The H plus will go on first. H goes where H is. Br goes onto the other carbon. So same structures here, still achiral, except now it's a bromine instead of an OH. Save room because, again, we're going to add 12 o'clock, 1:30, 3 o'clock, 4:30, 6 o'clock, 7:30, 9 o'clock, and 10:30 on our spiral around here. I do not understand why they call it a spider chart. I think a clock chart is a better name for it, but traditionally, chemists refer to this as spider chart. So we're going to start our memorization process and going to get highly organized. So 2 reactions down, 6 more to go on this one. And guess what? We're going to make another spider chart for alkene reactions because they do so many things. Okay, mechanistically, that basic concept of the first thing to go on, choose the less crowded side, and the second to go on, get stuck with the more crowded side. Occasionally, we end up having a reaction where both things are the same thing, so that doesn't matter. And that's something we're going to refer to as regioselectivity. I'm going to define that word in a few slides, but you choose the region. You choose the less crowded region or more crowded region double bond. But there's a second thing where we'll deal with the stereochemistry, and that's whether the two H's add on the same side of the double bond, so in front. So let's say my double bond is traditionally like this. So that's that. If I have my H here, if they add at the same time, then they do what's known as syn addition. They'll add to the same side. If they add one at a time, then one will go, let's say, to the less crowded side. The second one not only comes to the more crowded side, but it usually comes in from the back side, and they add on opposite sides of the pi bond. So we're introducing thoughts. Again, I'm going to go through all these a little bit at a time. So if it's too fast, no worries. We're going to redo this over and over and over. But this is what's known as syn addition, meaning synchronous. It adds to the same side. So Markovnikov, the first one we learned was a regioselectivity, saying H goes where H is. First one on goes to the more H or less substituted side. Second one on goes to the more crowded side. This case, we're not worried about that. H's, so it doesn't matter. H and H are the same size and going to have the same result. But what we do care a lot about is that they're adding to the same face. They're adding at the same time, so they add to the same side. So hydrogenation, we call it hydrogenation because it's hydrogenation. So hydration, we add water. Hydrogenation or hydrogenation is the addition of H and H. You possibly have learned this in either a general biology class or possibly general chemistry, depending on who your instructor was. But hydrogenation is a reductive process. The gain of H is reduction. The gain of O is oxidation. So hydrogenation, syn addition of hydrogen, reduces the alkene to an alkane. So you're going to hear that term. Reduction, hydrogenation is reduction of an alkene to an alkane. Important that you know that for biology. And so depending on, and again, I don't know who's listening, so it depends on where you went to school. Most of you, I'm assuming, will start out with just general biology, and they'll allude to it. Then you start getting upper division, you start covering things like molecular biology, microbiology, physiology, cell biology. And by the time you get there, you've learned this concept of oxidation reduction a few times, OChem, energy chem, so it makes more sense and they throw it at you. But if you happen to go to a school where they throw cell biology first semester at you, it's rare. Very, very, very few schools do this. But if you happen to go to one of those, then you may have learned some of your initial reactions, not necessarily in the same depth of nomenclature, names of knowing this hydrogenation. So if that's the case for you, the first time you're seeing it, this is a pretty important concept as you progress through biology. Okay. You can also add XX. So last time we made XBr, so I can add Br2, again, could be Cl2. You could even make it ClBr, IBr, different halogens, but halogen-halogen bond is relatively weak. Pi bond is relatively weak, so it's going to form a relatively stable compound in the end. Notice one is up, one is down. So whereas the same side is syn, opposite side, we already know the word, anti-addition. So when you see things that are syn, 99.99% chance both of the H's went on at the same time. So they both added to the same side. When they're anti, 99.9% chance, they went on one at a time. So when the first one goes on, let's say X, the red one goes on first to the less crowded side, it's going to hover above the ring system. The lower one will come in later on the other side. So again, let me draw the same orbital picture we had earlier. And it's very primitive at best. The X up here will go on. When it does, it becomes very crowded so that the other X can't fit in here as easily. So it has to come in from the bottom side. And so we get anti-addition. When one goes on, it crowds one side, so the other one has to go in opposite side. If they add simultaneously, you get syn addition. If they add one at a time, you get anti-addition. Okay, erasing everything again. Actually, I'm just going to erase that part. So the words can come in. So halogenation, you're adding halogens, is an addition reaction that adds two halides. Okay, this is an oxidative reaction because X is more electronegative than carbon. Hydrogenation reductive. We don't worry about this one in biology because if you're taking in Cl2 or Br2, you have pretty big biology problems. So we don't really have a name or common belief, I guess, I don't know, memorization system. I don't know what I'm looking for here word-wise, but hydrogenation is so common in bio that there's a word for it. Hydration, so common in bio, there's a word for it. Halogenation, common in OChem, not so common in biology. Okay, mechanism. Again, H goes where H is. So in this case, two H's and two H's, so I don't have a dilemma. H can go to either side. Um, I'm actually going to make it a little more crowded. I'm going to change my ways here and say, let's say we choose this side to have a CH3, which would mean this side right here, CH3. So now we do have a choice of one is more crowded than the other. You're ready for such a thing. So H wants to go to this double bond. We draw our mechanism where the electrons of the pi bond are going to come out and attack the H. When they do so, the H has a choice to be on the left, less crowded side, or right, more crowded side. H goes where H is, two H's on this side, one H on that side. And again, just talk about directly bonded to the carbon. Two H's here, one H there. So this pi bond is going to attack the H. The Br is going to break off. So this bond between the H and Br is going to get broken. When it does, that slow addition process is going to give you this compound, which is now, because I modified it, that. And so this carbocation now has a Br floating around from that. So the Br we just kicked off can now come in and attack. Kind of hard to break this and form this carbocation unstable. That's your slow step. So if you're doing an energy diagram, it probably looks something like that. High energy for the first step, slow energy second step. Low energy means very fast. High energy means very slow. So slow first step, once you get the carbocation, it's off to the races. You're going to finish with your final compound. Okay, have to know your mechanism. And you know what? These mechanisms are all going to start to look very similar. So learn the first one really well so that the second one comes a little bit easier. Learn that second one really well so the third one comes even easier. And by the time you're doing the fourth or fifth one, it's going to be a reflex. But H goes where H is. Okay, so asymmetric alkenes. That's back to what we were looking at earlier. CH3, CH3, ethyl, and an H. So I'm going to put my H here in green because green is for go, and H goes where H is. So the H in this case is going to go to the less crowded side. So in doing so, you're going to form this carbocation, which is tertiary, as opposed to this one, which would have been secondary. So plus charge here versus plus charge there. That is your driving force for this choice. You have a tertiary carbocation. That Br minus is now going to attack that tertiary carbocation. So the first slow step, forming the less H goes to the on first and choose less crowded carbon to form the more stable carbocation. H goes here, plus charge defaults there. Br then attacks. Same mechanism we just did before. Prettier drawing, computer generated, but same basic idea. And again, this is known as Markovnikov. My terrible writing, you can barely see the O right there, but that's a Markovnikov. Okay. So H gets stuck, or H chooses less crowded, Br gets stuck on the more crowded carbon. So this is known as regioselectivity, trying to decide which region, which side of the double bond it goes to. So the radioselectivity is known as Markovnikov. So now I don't have to write it so poorly. And then stereoselectivity, that's where you have a case of they go on opposite side, but because there's no chiral center here, no chiral center here, it's a moot point. So I don't care. I know it is going to do that. I know one side's going to become a little more crowded than the other. You'd have to look more carefully at the transition state because H is relatively small, but it's going to avoid this bulky group over here. So the BR is going to try to come in opposite of the bulky group here. So if this is sticking up, the BR wants to come in from below. But because there's no stereocenter here, we don't care. But just to be precise, I do want to draw it this way. So if I had this group right here, then the methyl group, it's going to stick out here. Keeping in mind this is trigonal planar. This is an empty p orbital. And the Br minus is going to attack that empty p orbital. So keep in mind that this is planar. I know I've drawn them vertical, but they would actually be in the horizontal plane, and it would attack top or bottom. So if I put it on top, hopefully you're sitting there, and I've drawn it out of convenience on top. If you're sitting there looking at this, like, wait a minute, it's going to run into this group here. So if I could actually track this, I would find, nope, my BR would want to come in from on bottom to avoid that bulky group on that side. So the BR would be on opposite side of that, which is kind of why I drew it that way instead of putting the BR up here. Okay, a lot going on. 2 more to add to your spider chart. Spider chart's filling up quickly. H2 hydrogenation. Oh, Markovnikov, need to add that word. Markovnikov here, but also need to add a couple more reactions, which I apparently am going to do next time. Sorry, I'm not familiar with how I divided this group of material up, but 40 through 42 all sort of tie together. Anyway, thank you for joining, and I will see you, as I always hope, at the next Toddcast. Thank you. Bye.